but I guess tonight might be nasty.
We are now. It's now. What is it? The 10:59.
Oh.
So we have 1 minute. Let me get this right. I tell you when exactly. Now it's 11.
To see.
Well, let's get started. It's such a joy today to welcome Jim Stone from the Institute for Advanced Study, and I think there'll be lots of exciting things to hear about. So,
Thanks, Morgan. So thank you for coming on a snowy day. So saying Morgan, it's been a very unusual winter in Princeton. We haven't had any snow at all. First time in recorded history, there's no snow by January. So this is great for me. I'm really enjoying this, but I understand totally it's maybe not the same for you guys. I would understand totally if you went skiing today and just skipped this, that's fine. It wouldn't bother me.
Stay with us.
Sorry?
You can
stay here.
The flight is delayed.
Yeah, I do miss the snow. So I thought I would tell you a little bit updating. This actually the first trip I've made since business trip since the pandemic. So it's great to be back here, visit with old friends and colleagues. And I thought I would tell you a little bit about what I did during the pandemic, actually, which is update Athena++ and tell you about some applications that I've been doing with this new version. It's a small audience. I hope this is very interactive. Please interrupt me. I may go fast or slow, depending on what I think you might be interested in. So just ask away. I thought I would try to motivate this by I think probably everyone in the room knows this, but exascale is here and it makes a big difference. And so I thought I would try to motivate that a little bit. And then tell you about this new version of Athena and some applications we're doing with it. Morgan said make this a 35 to 40 minute talk. So it means I'm going to skip one of the applications to try to fit everything in time. We'll see how we go. So exascale, 10 to the 18 flops has arrived. It's been 15 years, but the machines are now installed. The first machine frontier is at Oak Ridge, 1.5 exaflops, 1 billion times faster than the computer I used as a graduate student, just to make me an old, show what an old man I am. The 2 exaflop machine is coming later this year in Argonne, so there's going to be 2 of these machines in the US. And after 15 years to get exaflops, Intel's telling us we're going to get to zettaflops by 2027. I don't really believe that, but probably it won't be another 15 years before we're even at zettaflops. So things are advancing rapidly. And what does that mean? What does it enable? One thing it enables is ultra high resolution. For a long time, many people have been studying MHD turbulence in the interstellar medium, for example. Here's a calculation of supersonic turbulence in the interstellar medium using a resolution of 10,000 cubed. So that's pretty impressive, 12 trillion grid points with 4 orders of magnitude in scale in each dimension. Designed to try to reach the sonic scale where the velocity fluctuations are less than the sound speed on a small enough scale. It required 50 million core hours run on a year. This calculation was actually done before exascale, but it took a year to complete on those machines. Nowadays, you could do this in less than a day. You could run this calculation on an exascale machine in less than a day. So you could do many realizations of these kind of calculations. And here we know this is going on. So Math Liska has been doing these ultra high resolution simulations of black hole accretion. I thought I needed to show this movie in this local audience using this hammer code. Not quite the same resolution, only 5,000 by 2,500 squared. Again, made possible by a very large allocation on GPU accelerated machines. What's cool about these calculations is this movie doesn't really do it justice. You can zoom in by much more and see this tiny thin current sheet forming just outside the event horizon in the so-called MAD state, which is producing reconnection and plasmoids. And the good news is with exascale and multiple GPU accelerated GRMHD codes available now, these kind of calculations become much more routine, and we can investigate this kind of physics and scan parameter space much more easily. So I think that's exciting. I should also, though, I might get on my soapbox and say that not every calculation requires exascale and super high resolution. Yes?
Can I ask you?
Yes.
So you can run the simulation a day
Yes.
How many weeks do you need to download the data?
Well, exactly. The analysis, of course, takes much more than a day. You never download the data. That's impossible. You have to do the analysis remotely on the remote machine. But writing the scripts and figuring out what to query, what questions to ask of the data, that's, of course, the challenge. Sorry?
It's like an observer.
It's like an observer, exactly. It's so bad that actually sometimes you can't even keep the data. That if you finish the run and you forget, oh darn it, I should have plotted this variable, you just go back and do the run again because it's much cheaper than trying to keep the data and post-process it. So yeah, there's definitely issues involved in this. So I wanted to make the point that if you don't have access to exascale and you're not doing gigantic simulations, that's fine because there's lots and lots of physics you can learn at much, much lower resolutions. And I would point out that the original three-dimensional MRI simulations done by John Hawley using an astounding resolution of 31 by 63 by 31 grid points in 3D. Nonetheless, the basic properties of the nonlinear regime of the MRI emerged from that calculation. Namely, you saw the transition to MHD turbulence in the nonlinear regime, and even things like the magnetic stress produced in the simulation was proportional to the magnetic field strength. There was this plot. The points were individual simulations. They followed this beautiful scaling in which this proxy for stress versus vertical magnetic field showed this clear power law scaling, which has stood this test of time. That's still true at ultra-high resolution. And even today, in just last year, there was an interesting paper by Mitch Begelman, Phil Armitage, interpreting this result from 40 years ago in theoretical analysis. So there's still lots to be learned, even at low resolution. You don't need ultra-high resolution for everything. The other thing the exascale enables is much more accurate algorithms, because they're generally much more expensive, and so they're harder to run on smaller machines. And so, for example, higher order, say fourth order algorithms for fluid dynamics, they're typically 4 times slower than typical second order algorithms, but it makes a difference. So here's a plot showing the time evolution of the Kelvin-Helmholtz stability for a calculation done with a spectral code called Daedalus, using 4096 spectral elements and explicit viscosity and heat conduction. So this is a resolved simulation showing you the transition to turbulence in the nonlinear regime for KH instability. And if you increase the number of spectral elements, you get exactly the same solution. Here's the same calculation done with a fourth order algorithm implemented in Athena. And you can see pixel by pixel, you get exactly the same solution. And you can even take the difference between the solutions and calculate the L1 error norm and plot that versus time, and you can see how the solution converges to the exact solution. You get L1 error norms down to the round-off error of the data. And so this fourth order algorithm is giving you spectral accuracy, if you like. It's giving you the absolute resolved solution for this nonlinear turbulent flow, but at much less cost because these finite volume methods on parallel computers are much, much more efficient than spectral methods. So higher order methods can give you spectral accuracy, which is great. And these larger computers allow you to afford it. And it makes a difference. Elias Most has been doing neutron star merger calculations, and he's shown results both using fourth order methods for the fluid dynamics and second order methods for the fluid dynamics. And you see much less diffusion of the atmosphere of the neutron star before merger at higher order. And you see differences in the magnetic field resulting from the turbulence and the plasma beta that results from the turbulence when you compare the fourth order method to the second order method. So I think another exciting direction to go is more accurate algorithms that are made affordable by having more powerful computational tools. And of course, the other thing exascale enables is additional physics. There's many problems in astrophysics where we know we need to go beyond just fluid dynamics. We need to add radiation or neutrino transport, plasma physics, dynamical spacetimes, blah, blah, blah. Everyone has their own shopping list of things they'd like to be able to add. And so it's exciting times because those sort of things are becoming within reach. Although developing the codes that solves all these systems is still a tremendous amount of effort. I mean, there's much to be done in algorithm development and building tools that are able to explore these sorts of things. So this is basically the motivation for considering a new rewrite. But the challenge, a new rewrite of Athena, but the challenge is that these computers use very heterogeneous designs. They're not all the same. So if I take 4 of the largest computers available in the world today, for example, Fugaku in Japan has 1.6 million ARM processors. They're basically standard C processors, except they're very simple instruction sets, so they have to be programmed a little bit differently. The three machines in the US, Frontier, Aurora, and Perlmutter, they're all using GPUs to accelerate the performance, almost exclusively because GPUs are more power efficient. I mean, the only reason GPUs are interesting is because they're more power efficient. And when you want to build a big machine, the limiting resource is electricity, and so you can get more processing power per watt if you adopt something like GPUs. But the issue is that the Frontier uses AMD GPUs, and Aurora uses Intel GPUs, and Perlmutter uses NVIDIA GPUs. And you say, oh, who cares? A GPU is a GPU. But no, they all use different programming models. You can use C++ on Fugaku, but AMD requires you to use HIP to program in their GPUs. Intel wants you to use SYCL. NVIDIA, of course, wants you to use CUDA. If you write your code in CUDA, it will not run on the Intel or AMD GPUs. And so that's a real problem for application scientists, because for people like me, I don't have the resources to support a different version of my code for every different machine that I want it to run on. I just want to build it on my laptop and run it wherever I want to run it. And so really, progress is being limited by not having a single programming environment. There are emerging standards like OpenMP and OpenCL, but it requires a vendor to adopt those standards, and they've been slow to do that. So what's been really interesting in the last 5 years, I think, is the emergence of this new C++ library called Cocos, an open source library that basically acts as a translator. It takes your C++ code and it translates it into CUDA if you compile it for a CUDA machine. Or it'll translate it into SYCL or HIP or whatever you want, or ARM. It doesn't matter what architecture it is. This library supports it. You'll be able to run your code on that machine. So it's a very, very attractive way to write portable code. It does build in a dependency on the Cocos library, but that library itself has no other dependencies. It's just a C++ package that you install, and then you're able to program and run on anything. So that's what we've adopted. I think it's a very, very attractive way to go. I mean, which way to go is another important issue. I'd be happy to talk about it. There's pluses and minuses with all these approaches, but so far, Cocos has worked extremely well for us, and I'm very, very impressed with what it can do. So what did I do when I was locked up for 3 months like everybody else? So rewrote Athena++ into Cocos. It's a complete rewrite from scratch. Has the full AMR framework, the octree block-based AMR framework. Continues this dynamical execution via task list to give you very good performance on large numbers of processors. And over the last year or so, we've been getting lots of physics built on top of that framework. We have relativistic and non-relativistic hydro and MHD, both in special relativity and GR. We have dynamical spacetimes now, I'll tell you about that a little bit later, and radiation transport, diffusion, and so on. It's restricted to Cartesian coordinates only. We're not doing curvilinear coordinates for reasons I'd be happy to discuss, but I think that's the right way to go. And it runs on virtually any hardware using Cocos. In fact, it'll run on your iPhone if you want, because that's just an ARM processor. And so they have a back end for the A15 processor that's in your iPhone if you want. I haven't done it yet, but I think it could be done. And you get really excellent performance and scaling on whatever architecture we've tried it on. So on both NVIDIA and AMD GPUs, Crusher is a machine at Oak Ridge based on the AMD GPUs. So what's plotted is the performance on a per GPU as a function of the number of GPUs you're running on, out to about 22,000 GPUs here. And for good weak scaling, it should be a flat line, and those are awfully flat lines. It's about 95% efficient out to 2,000 GPUs, which was as many as we could get on these two machines. So it's essentially perfect weak scaling on those machines. And the individual performance is also very, very competitive. It's extremely close to what other reported performances are on these architectures. So I think we're in really good shape for being able to exploit these machines using this kind of programming module. I should say, this is not trying to replicate all of what's in Athena++. Athena++ is an open source code that continues to be developed by lots of people and used for lots of things. This is really targeting performance and scalability in exascale HPC. And so it's not going to have all the functionality of Athena+ ever, because really we're trying to aim for large calculations that can only be done in exascale with very specific tools that allow, or physics that are interested on those scales. And I should also mention that there are other efforts to do the same sort of thing. And so in fact, there's something called the Parthenon framework, which has taken the Athena++ AMR framework and rewritten it in Cocos without any physics solvers, just the AMR framework. It's being led by Philip Greek and Josh Dolans at LANL. And that's it's an open source effort. You can look into Parthenon if you need an AMR framework running on Cocos as a potential way to go as well. Okay, so that's enough about the methods. I thought I would say, what are we doing with this? And I thought I'd talk about two science applications. One is how to feed black holes in elliptical galaxies. How to get the material from kiloparsec scales down to AU scales and ultimately the event horizon in galaxies like M87. Right? We have this gorgeous image from the Event Horizon Telescope for M87 as well as Sagittarius Star. Of course, that's extremely small scales. In intermediate scales, we observe the jet, we observe there is gas there, and of course we have images of the whole galaxy. Something's going on to get this plasma down to the event horizon, and how that happens and how much magnetic flux it carries with it is very important for interpreting and understanding the images that are being generated on these very, very small scales. So we thought we would do some numerical experiments following previous work to see if we could understand this process. Our experiment is to take a hydrostatic equilibrium and a galactic potential, take the realistic dark matter potential of M87, put in a fluid in a hydrostatic equilibrium, including cooling and feedback heating to give you an equilibrium state, provide some turbulent velocity fluctuations to the initial conditions. Could have been generated by substructure, could be generated by type 1a supernova, which are going off in the galaxy all the time. See what those turbulent velocity fluctuations do to the thermal instability that's generated from the optically thin cooling, and see how this multi-phase medium evolves in this galactic potential and studying the infall and accretion of hot and cold gas. Yes. The jet is not included here. Of course, that's ultimately going to interact with the gas as well, but we're assuming that's sort of a pencil beam coming out in some angle, and we're only worried about sort of spherically average dynamics as a first step. In future work, one might consider how the outflows and jets feed back directly, but that's not here at the moment. Okay, so what's unique about this calculation, I think, is the ability to go over 6 orders of magnitude in radius, from 30 kiloparsec scales all the way down to about 100 RG, just outside, within 2 orders of magnitude of the event horizon. And what's plotted here are time scales versus radius. So for example, the cooling time is the blue line in the initial conditions, and the black line is the inflow time, how long it takes gas to fall into the center. And you can see the cooling time is much shorter than the infall time beyond about a kiloparsec. So that's where thermal instability is going to produce a multi-phase medium beyond a kiloparsecs or so. And then we're interested about how those cold clumps formed by thermal instability fall in. And to do that, we start with a calculation which extends about 3 orders of magnitude in radius. We allow the thermal instability to develop over a few 100 million years. And then we extend the calculation using AMR to ever smaller radii. Of course, as you go inwards, the timescales get much shorter and shorter and shorter, and you can't continue to integrate it for hundreds of millions of years, but you can integrate it for many, many, many dynamical times of the inner region, with the outer region giving you the self-consistent boundary conditions for the inflow. So this is the moral equivalent of the zoom simulations that people do in cosmology to sort of zoom into galaxy formation. So what happens? Invariably, we see these 2 kinds of inflow produced. This always emerges from our initial conditions. You either get this cold, chaotic accretion flow, which has been described in literature by Lee and Bryan and Gaspari and others, where you have dense blobs falling in from random directions and sort of interacting in a very complex, chaotic way and generating a highly turbulent, clumpy medium. This is a volume rendering of the inner 2 kiloparsecs of the flow, with the inset, which you can barely see, being yet even smaller region on the center. Or, depending on sort of random chance, if the velocity fluctuations at large scales have a lot of specific angular momentum, then as they fall in, they form a rotationally supported disk. And so the other alternative type of flow you get emerging is the disk. And it can switch between the two back and forth. You get disk-dominated accretion to this cold, chaotic accretion in the flow. No, not in MA7. We don't see it.
So
Yes.
that's wrong.
Well, wrong. I mean, it just means it's not currently occurring in the disk. This could happen in MA7 if you produced velocity fluctuations on the outer scale that had the right enough angular momentum, right? It's not wrong, it's just not present in M87. I'll bet there are other elliptical galaxies where you might see this.
Can you tell what it depends on, which scenario you get?
Sorry?
Can you tell from looking at the galaxy which state of the accretion will produce?
I mean, the way to tell would be whether or not there would be a disk in the gas. So if you see a disk, then you know that's emerged from having a more specific angular momentum in the gas.
But are there any macroscopic properties that tell you which state you'll end up with in the center?
So in these hydrodynamical calculations, I think the only switch between these two is whether or not there's mean angular momentum in the background state, which, given some random realization of the velocity field, may or may not occur. It all depends on what the driving is doing. For that, you need to put in the type 1a supernova and do the driving self-consistently and see what the actual mean momentum is. So you can zoom in and look at the properties of these flows in the so-called disk state, which actually occurs in the vast majority of the time for the particular realizations that we've been doing. So you get a very, very dense, cold, thin disk. The bottom panel is the Bernoulli parameter. If it's negative, it's bound, and positive, it's unbound. And so the disk itself is cold, rotationally supported, bound gas. And at smallest scales, the disk is actually not contributing very much to the accretion on the central object. It's all coming from the hot medium, the hot gas, which is the volume filling intergalactic medium in this galaxy, and that's the stuff that's mostly falling in. Similarly, in the cold chaotic accretion phase, you don't see a disk on the larger scales, although when you zoom in to sub-parsec scales, once again, a small disk emerges. Again, cold and bound, but the Bernoulli parameter is negative. And again, now accretion is still being dominated by the hot phase. So no matter which phase you're in, the cold gas is not really making its way in. Of course, these are hydro simulations. If you added magnetic fields and resolve the interior of the disk, you might get actual mass accretion through the disk through angular momentum transport due to MHD turbulence, but that's not in these particular realizations, these calculations. And you can look at the time average. Yep.
Even the hot medium will have some angular momentum.
Yes.
Somebody has to remove that angular momentum for it to accrete. How is it happening in your simulations?
So the amount of matter that actually falls in is extremely small because of these radial scalings. So all you need is a tiny fraction of the gas initially to have very small angular momentum, which it always will. That stuff can make it in. Along the way, it can experience torques from pressure gradients. I mean, it is a complex flow. You can have material which is merging and, colliding, if you like, and canceling its mean angular momentum. So there are hydrodynamical processes which will result. I would imagine there's a PDF of angular momentum. And there's some small fraction of the gas which has extremely small amounts of angular momentum, and that's more than enough to account for the actual mass accretion rate in the center, because that's so small. The actual mass accretion rate at the center is varying like the square root of the distance. And so at the event horizon, the amount of matter actually making it all the way into the center is just exceptionally tiny. And it's probably set by this physics, by the fact that the amount of material which has the small enough angular momentum to make it in the middle is just very, very, very small. So if you're accreting a lot of material, I would say that you're right, there's a problem there. But the fact you're accreting such a small amount is. Yeah, so the other thing that emerges is that the density, temperature, and mass accretion rates follow these nice power law scalings over very, very large ranges. Density going R to the minus 1, temperature R to the minus 1. You can see the cold phase is pretty much frozen at the stable cold phase temperature. The hot phase is in the red line following this power law. Interestingly, the emission weighted temperature that you would actually observe is pretty constant in agreement with what you might observe for an elliptical galaxy, so that's reassuring. And moreover, the mass accretion rate that actually makes it to the horizon is bang on what you might expect for M87. And so this mechanism seems to be able to provide just the right levels of mass accretion and moduli the fact that we don't have MHD and that we're initializing the turbulence in some random way as opposed to a physical mechanism for driving it seems to be quite applicable to M87. So student Minghao Guo has been working on this, and his next step, I think, is to do the same kind of calculation with MHD, because not only do you want to know how much matter is making it into the middle, you want to know how much magnetic flux is making it into the middle, because that's very important for determining how much outflow and feedback you're going to get from the center. And so with MHD models, we hope to study the inward transport of magnetic flux by similar processes. We want to move to full GRMHD to look at the feedback. It's an obvious question, and then you'll be able to generate jets and see if you can understand how that might feed back onto the flow at intermediate scales. And as I mentioned, we think we can guess or we can work out what the dominant driving mechanism should be in M87. It's probably type 1a supernova. And again, we can put that in directly, modeling the supernova driving of the turbulence. Yes?
One additional thing that you might want to include here, a bullet, is because the temperature goes as 1 over r, and the density goes as 1 over r.
Yes.
The Coulomb-Winfrey path will become much bigger than r, close to the center.
Right.
So obviously Coulomb collisions are not making it a fluid, and the question is whether the electron and proton temperatures are the same.
Yes. This is an outstanding question in these low luminosity accretion flows, is whether you need two fluid MHD and whether or not the electrons and ions are coupled. So this model is fluid dynamics only. That's definitely a more advanced step, I think. I think just trying to understand the MHD processes that can lead to the scalings that we observe, I think is already a big step for the student to work on. Yeah, so this is going to be their thesis work, and stay tuned for more applications. This is a high-level discussion overview, I guess, of this work, and there's a full paper on the archive if you want to know more about this. But I thought I should move on to a second application, something related but somewhat different, which is to now zoom out all the way down to the event horizon to look at the structured accretion flow around black holes on small scales, and primarily focus on not M87 and Sag star, as interesting as they are. Those are low luminosity sources. Actually, I think the AGN quasars, X-ray binaries, where the Eddington ratios are much higher, are just as important and very interesting to study. But in those regimes, we know you have to incorporate the radiation feedback, because radiation completely dominates the dynamics. The radiation energy density exceeds the gas energy density. And really, you need to model the radiation hydrodynamics of those flows. And so this is a regime that has been studied quite a bit in the past. There's been a lot of work using moment-based methods, particularly using this M1 closure for doing radiation transport in full GR, including many people here at CFA at Harvard. So Jonathan McKinney, for example, Oleg Sadowski with Ramesh has worked on this a lot. Matthew Liska now is working on this as well. So they're doing the full GR-MHD, but incorporating radiation transport using these closure methods, M1 in particular. And in addition, I've been involved in work with Yanfei Zhang and others in which we're doing the full transport of the radiation field. So we're solving the transport equation, but neglecting the GR. It's all been done in post-Newtonian or pseudo-Newtonian potentials. So the idea here was to try to bridge this gap, use full transport algorithms for radiation transport, but do it in full GR. And that's where we are now, is working on this. So, one technical slide for the experts. So what's novel here is that we're solving the covariant transfer equation for the radiation-specific intensity I, and we're using a form of the equation that's written out here that, without going into details, you can just see by inspection that this is a hyperbolic PDE. It's the time derivative plus divergence of fluxes is equal to source term on the right-hand side. And that looks just like the equations of fluid dynamics with the addition of these source terms on the right-hand side. That means you can leverage all of the numerical algorithms that have been developed for fluid dynamics to solve this equation. So you can use higher order finite volume schemes for updating the specific intensity, which guarantees exact conservation. It's very important for conserving radiation energy density. You can use higher order up-scheme methods. So that's one novel approach. And it was really Davis and Gamy that sort of worked out the covariant transfer equation in this form that allows you to leverage these numerical tools. And the other novel aspect is when we switched to using this geodesic mesh in order to discretize the specific intensity. So within each spatial grid cell in the domain, you have to discretize the specific intensity I over the full 4 pi steradians on the sphere. That's those coordinates zeta and psi in the transfer equation, the angular coordinates of the radiation field. And to do that, we're using these geodesic spheres, which have much better coverage, more uniform coverage of the sphere than doing latitude longitudinal meshes like we were doing before. They're a little more complicated to implement, but they are, I think, much better suited to this problem. So the method is described in this paper, just appeared led by Chris White, and it's well tested. We've done, beams in spinning spacetimes around Kerr black holes. So here's the green lines in the analytic geodesics followed by photons from a radiation that's sourced in the sphere, and the colors of the result from the transfer solver. We've done linear wave convergence tests. These are really tricky in full transport. Because there's no analytic solution except in the Eddington approximation, and forcing that in a full transport method is interesting. So a lot to be learned from linear wave testing, in fact. And there's a whole slew of tests, and I won't go into much more details, but it's all implemented and working in both Athena++ and in Athena K, this Cocos version. And it's the Cocos version I'll start showing you some results from now. We are using a Cartesian mesh, which is somewhat different than most people doing GRMHD are using spherical polar meshes. And of course, you may ask, well, does that work? Can you really use Cartesian? So without radiation, we first ran some standard, for example, MAD initial conditions with spin, and using a nested meshes, which has overlaid the solution. There's a poloidal and a equatorial slice, and you see the formation of this powerful jet. Everyone's going to immediately focus on the glitches in the funnel region at mesh boundaries. That's a bug in the plotting software. It's plotting a slightly different slice in the direction. It's actually not in the real data itself. It's in the plotting. So trust me, you can ignore that. So you see these emergence of bubbles, and they're mixing in the equatorial plane. Qualitatively looks extremely similar. If you want to focus on the funnel region, the thing to focus on is this scale. It's 9 orders of magnitude. We've managed to figure out ways to avoid using floors in the funnel region, using special techniques for fixing up the funnel region. And so we're actually able to evolve the funnel region directly. And so there is actually mass in there and structure. It's actually problematic because in MHD, it's probably not the right model to be using at such low densities, but it's an interesting thing to pursue in the future as to what physics to put in to model that region properly. We've also done the standard EHT code comparison project, which is a sane evolution, and the GPU version is this dark blue line, which sort of is the median of all the other codes. We're bang on what everybody else is doing for the EHT code comparison. So these Cartesian meshes, I think, are another attractive way to do 3D GRMHD because they have some advantages, especially for studying the flow at larger scales. They seem to work very, very well. So let me show you some, this is very much work underway. So I'll show you some very low resolution preliminary results just to whet your appetite, and hopefully we'll have much more in the future. These are low resolution comparison of so-called fishbone-Moncrief torus with no radiation at all, and then the exact same initial conditions where we replace some of the thermal energy with radiation energy density in a very optically thick disk, appropriate for roughly a 10 solar mass black hole. Initially, the radiation to gas pressure is around 1,000 in the midplane, and we just let it rip, see what happens. And the first thing that happens, the movie kind of evolving slowly, is that you immediately see a wind being generated from the radiating disk case. It's because this radiation field is filling this cavity region. You can see that the flow is following beautifully the edges where the boundary of the radiation field is. So you're blading a lot of material from the radiation field. Eventually, however, that MRI develops in the midplane. You get turbulence and accretion. Even though this is formally sane, it generates a a jet in the middle after a while in the no radiation case and in the radiation case, in fact. And then it sort of settles into, if you compare the solutions, they don't look that much different. There's a much wider opening angle here compared to there in the funnel region. The movie's going to go on for a long time, and we're all going to get bored watching it. So let me just jump to what are, if any, the interesting differences at this resolution. And in fact, there are already some very interesting things going on. So first of all, I already mentioned this radially driven wind coming from the torus that you don't see in the non-radiating case. The radiation pressure continues to completely dominate the dynamics. This is the ratio of gas to radiation pressure. It remains 10 to the minus 2 to 10 to the minus 3. In fact, it drops down to even in this cone region where the photons are radiating from both sides of the funnel. The highest radiation energy densities are right there in the middle where everything on the axis is being irradiated. So there's extremely high radiation pressures just above the black hole in the funnel region. The radiation field itself, as you would expect, is isotropic. So this is this C parameter is the magnitude of the radiation flux divided by CE. Where that is 0, it's isotropic, and where it's 1, it's completely beamed. So this is 1 to 0. So in the midplane, it's basically 0 and fully isotropic. But along the poles, it's highly beamed, as you would expect. Again, because the photons are coming from both sides, irradiating the walls, and the only way out is out the hole. Maybe the most interesting thing, or two of the most interesting things, is that the Lorentz factor in the jet is much lower in the radiating disk case. This is not surprising because there is very strong radiation drag. The jet is trying to propagate through the regions of highest radiation energy density. There's a very large radiation viscosity, which is trying to prevent the jet from moving. And so, interestingly enough, in the radiating case, the jet gamma is around 20. It's only about 2 in the radiating case. That's interesting.
And it's not the mass loading of that region?
It's not the mass loading because they both have extremely low, sorry?
That's super interesting.
Yes.
So the wind then comes off only at those angles?
Yes, the wind is not making it to the axis. I mean,
Yeah.
basically no plasma can ever make it to the axis because you have to have zero angular momentum to get there.
Okay.
And that's really, really difficult.
And you have radiation viscosity
Yes, because,
in the code,
well, it's in the equations.
in the equation.
So since we're solving the transfer equation, then the radiation pressure tensor has both diagonal and off-diagonal components. And so yes, where the radiation field is there is radiation viscosity. You can't avoid it. It just comes out of the dynamics. In fact, probably viscosity is also going to be important in the coronal regions, but it's only important where the optical depth is relatively low. If the mean free path of photons is short, you're not going to get very much viscosity. So I don't think it matters in the disk midplane. It's where it's basically isotropic. It's really only important in that funnel region. And there, it might make a difference. And the other thing that's happening is that the magnetic field, and this has been known from previous calculations, it saturates not at the gas pressure, but it saturates at the total pressure. And that's much bigger than the gas pressure. And so when you calculate the ratio of gas to magnetic pressure, that number is sort of unity in the midplane with no radiation because there's only gas pressure around, and so the magnetic field just saturates at the gas pressure. But notice it's mostly red. That is to say, beta is usually very, very small in the disk midplane in the radiating case. That's because the gas pressure is much smaller than the radiation pressure, and the magnetic field is being amplified up to the total pressure. And so that's potentially very, very interesting. Namely, the properties of the MRI turbulence and the nonlinear regime care about whether or not there's radiation or not. And it might be different transport in these two regimes. So even though these are low resolution calculations, I think these sorts of things are emerging already. Okay, so I said I would try to keep this short. And we have like many people, we've been very lucky to get some large allocations on these exascale machines I was just talking about. We have a ton of jobs in the queue right now. I wish the queues were faster and I could show you a lot more. But literally, the jobs are in the queue, and we're doing all of these calculations at much, much, much higher resolution. This was all done on our local 4 GPU cluster. And so now, when we're doing on 2,000 GPUs, We're going to have lots and lots of results in the future, and we'll help tell you a lot more about what we see emerge from all these calculations. But let me just tell you about one other cool thing we've been doing, which for me is something completely different. There was a GR numerical relativity solver built on top of the Athena++ AMR framework called GR Athena++. It was implemented in C++, and it just uses the AMR design of Athena to solve Einstein's equations using the so-called Z4C formalism. So in the, last year, working with David Rodice at Penn State, we've moved that to the Z4C solver using Cocos in Athena K. And we now have binary black hole evolution in full numerical relativity in Athena K on multiple GPUs. So for example, here's a calculation. It has 9 levels of AMR, 6th order in space finite differencing in Z4C, 4th order in time. It runs in only 10 hours on 2 GPUs. And we can see, zoom in, the binary black hole merging, ring down. You can see the contours of chi have these quadrupole, the wave emission. I mean, I wish I could show you the actual gravitational waveform, but extracting the gravitational wave signal is extremely complicated in numerical relativity and is a diagnostic that we have yet to build into the code yet. So all I can show you is the actual evolution and ring down. So what's interesting about this is that because this code is so scalable and we can run this in exascale, it can reach regimes that would be previously inaccessible. We can do mass ratios, for example, of 10 to the 4 in the black hole, binary black holes. We can also do hyperbolic orbits and hyperbolic encounters. My interest is in doing the gas dynamics. So I'm interested in doing some accretion onto binary black holes in numerical relativity to look at how that might affect things. And that's on there's a student, Henry Hugh, in the physics department working on this with Franz and I, and we expect to have lots coming out soon. This is really, just last week, finally got the whole thing to fully.
X and Y, because now it's GR.
Well, this is at infinity, it's still X and Y.
Okay.
Right. Okay, so I'll wrap up there by just saying that I probably didn't need to convince you of this, but exascale is going to allow lots of interesting things. Despite the death of Moore's law, computers continue to get much, much more powerful, and we're going to be able to do a lot of things with it. And I think Cocos is a very powerful way to exploit these new machines. And I told you about 2 applications we're working on, and I have a whole shopping list of other things that we'll work on. So I'll quit with that. Avi and
So you mentioned that as you improve the resolution, you get convergence. But
Yes.
some problems have chaos.
yes.
Under different slight perturbations, you get different outcomes. So you will not necessarily get convergence.
No.
Statistically speaking, you might.
Correct. So in any problem that's chaotic, then talking about point-wise solutions is meaningless.
Right. So did you?
So the only thing you can study is the statistical properties. And so, for example, hydrodynamical turbulence is a good example of
Right.
chaotic flow. So
Right.
now I showed you an example of the Kelvin-Helmholtz stability. How do we get convergence there? Well, that had explicit viscosity and conduction and so on. So the solutions there are not chaotic, and there is convergence to a, quote, correct answer in that problem for a finite Reynolds number. But in general, if you're looking at some turbulent flow in multi-dimensions, then it'll make a difference. So the only thing you could talk about is statistical properties. The MRI is a very good example. There's a classic paper by John Hawley where he simply recompiled his code. He didn't change a single thing. He ran the code on one machine with one compiler, say Intel compiler, then he recompiled it with a GNU compiler, ran exactly the same problem, and then 100 orbits you get a completely different solution. Yes?
Can you talk about your plans for TDEs?
So yeah, of course, the radiation transport is very useful for that problem. So the idea would be to focus on the very central regions, looking at the. So I'm working with a member at the institute in which we're looking at emission from objects that are just outside the Roche radius and are transferring mass as they pass within the Roche radius, and then we're following the motion of that mass inwards to see whether or not it makes a disk, and if it does, how this stream interacts with the disk, and then ultimately try to compute light curves from what that might look like, because there's some very interesting sources that are seen in Assassin, for example. There's quasi-repeating sources that may be this model. So of course, these kind of approaches are, modeling an extremely eccentric orbit is extremely challenging because of the length scale, so it's much better for us to start with problems where we can focus in on the inner region, and these kind of sources are an ideal example of that.
But do you, I mean, with this exascale capability, do you have like future plans to think about the global problem and parabolic encounters?
It's certainly on the table, but as was pointed out earlier, you have to be committed to a problem before you try running on an exascale. It's not something that you're going to do in the next 15 minutes and get a run. So yes, if there's a problem where you feel like the only way to get the meaningful solution is at exascale with that kind of resolution or that kind of physics, then absolutely it's on the table. You could imagine it. But I think in the TDE problem, there's a bunch of simpler things to go after first. And then in the future, as needed, I think one could imagine going after those things. I would say what's exciting is that with exascale and with better codes, these things are within the realm of possibilities now. But I wouldn't necessarily say that's the first thing to do. Ramesh?
Yeah, so Jim, on the exascale business, there's something that I feel I'm missing. So computers are not getting really, individual processors are not getting that much faster.
Yes.
Right? The way we buy the exascale is by having massively parallel, a zillion GPUs, etc.
Right.
etc.
Right.
Okay. So exascale allows you to increase resolution, quite significantly, as
Right.
you've shown. And let's say I've got a physical problem, and I now can squeeze many more cells into my zone of interest. That means my cells are getting smaller, and therefore, Courant condition, the time step becomes shorter, real physical time step.
Yes.
So it seems to me that I can put all the resolution I want using 10 to the 12 processors or whatever. End of the day, if I want to run my problem for a certain physical time, and my time step gets shorter, and my processors are not faster, it means I also have to run it longer. Am I missing something? So, like for instance, Jamie's question about, can we do a global TDE, which has got, these vastly different
Right.
time scales. That's hard enough at low resolution, it seems to me. If you want to now do it with the exascale,
Right.
how do you beat this time constraint?
Right. So I would bundle it all together, right? So that an explicit algorithm for fluid dynamics, the cost scales like the fourth power of the resolution, where the extra factor of 2 comes from the time step. So yeah, from going from, for example, from exascale to zettascale, a factor of 1,000, that doesn't even buy you a factor of 10 in each dimension because of this scaling of a factor of 4. However, I would say that the processors are getting simpler, and therefore they work on smaller chunks of data, and therefore you can use more of them. You can exploit the whole machine and evolve it more quickly per time step to longer times. That's limited. Of course, once you get down to 8 grid cells per processor, you can't get much smaller than that. And at that point, you will be limited in wall clock time and how. But we're not there yet. We're not at the point where we're using the smallest number of grid cells per processor that we can possibly use, and we just can't make things any faster than that. That will be a limitation for, in other words, going forward 50 years from now, are we going to be able to evolve things for cosmological timescales? Forget it, because of this precise limit that you've mentioned. And I would also say that, remember I talked about 3 things being interesting about exascale, and resolution was only one of them. So this radiation hydro algorithm, it requires 100 times more variables per cell than does MHD. So now my problem has got 100 times more expensive. Actually, turns out it only ends up being about 5 or 6 times more expensive when you work out exactly how many floating point operations there are. So what exascale means is I can do that problem for free. Rather than just doing my hydro with some resolution for some time, I can do GR radiation hydro for the same cost. That's enabling, I think. In addition, you can also increase the accuracy of the method, basically for free. So while I was only doing 100 cube simulations, and maybe you can only still do 100 cubed, you can use a fourth order algorithm and make that like the accuracy of a 200 cubed, basically double it. So again, that's another way to essentially double the results that you're getting out of it. So I think there are ways to improve it. A really important point, I think, is that the improvement in computation is not driven solely by computer hardware. In fact, that's the least most important part of the development of computational astrophysics. The improvement in algorithms by far beats that. In other words, going from an order n cubed algorithm to an n log n, and going from an n log n to an order n method, which seems like a tiny change, but that alone far outweighs Moore's law in terms of what you can solve. And so, have we found the most efficient, best way to solve rate of transfer equation, do neutrino transport, GR? I'm not sure. There could be better ways to do it. And those ways will enable us to do much more interesting physics, I think, in the future than just the raw increase of power of the actual hardware itself.
Thank you.
Yeah. Andy?
I was wondering about plasma physics. You reach scales where the mean free path becomes longer than the grid cell.
That's for these low luminosity sources, yes.
And okay, you always have the excuse of magnetic fields lowering the mean free path, but that depends on the topology, and it's a bad excuse unless you do it really and show this.
Right.
So I wonder, isn't that a problem in the sense you need to replace your hydro simulations now with real plasma physics prescription?
There are some aspects of plasma kinetics where you're absolutely right. The fluid dynamics is not a good approximation, and you would need to consider kinetic effects. And there's in fact considerable interest in this as applied to the interpretation of the HT images, where it's pretty clear that it's a two fluid already, electrons are different temperature than the ions and so forth. Does that mean you have to go all the way to pick? That's very much an area of active research. Ramesh and I were both just at the same workshop a week ago, and again, you can correct me if I'm wrong, but one of the messages from the card-carrying plasma physicists was that probably the best way forward is simply to adopt kinetic closures in MHD, add in anisotropic viscosity and heat conduction in a fluid model, and that probably captures 90% of the kinetic physics that you need to worry about in weakly collisional plasmas.
Rogensky equations, basically, from 1965.
Except you need a closure for the it's basically that. Actually, CGL is even better with this Landau closure for the heat fluxes. That's the best way to go. But yes, basically the same philosophy. And because the magnetic field is very powerful in preventing the particles from just going wherever they want. They are forced to stay on these very small scales. And then moreover, you have these wave-particle interactions. Coulomb collisions are one thing, but in fact, it's the interaction of the particles with fluctuations in the magnetic field that are most important for scattering them and isotropizing them. And so there's all these kinetic instabilities that drive everything back to Maxwellian. As much as they want to be completely free to do what they want, the magnetic field prevents that from happening. There's fire hose and mirror modes which force them back to isotropy. And so these are all captured in these kind of kinetic models. So that gave me a little bit of hope. I mean, maybe Ramesh, you were...
I got even more hope.
Okay.
Because what they showed, at least people were saying, that even in regimes where you think MHD shouldn't work, it's a surprisingly good description
Well,
of a more complicated
if they
system.
were correct, then we would have fusion reactors working by now, but we don't. So there is more to the instabilities than they're willing, maybe the 10% that you were, 90% it's right, but then, tokamaks show us that we don't fully understand these instabilities.
Well, absolutely, but for the astrophysical problems,
Maybe it's
what one is finding is given the...
The only pushback, I think we understand them, we just can't control them. I mean, I think they know that these disruptions in tokamaks, they pretty much know
okay,
what...
can you simulate that for them?
not me personally, of course, but yeah, the people at the lab, you know, they use these gyrokinetic and so on models, and they even try to build feedback models to control them. It's an engineering problem where, you know, they know this plasma is unstable, and building a machine that controls those instabilities is the issue, and how to stop it once it goes. But I'm not trying to make light of how challenging a problem it is, but I think maybe it's more an engineering than a fundamental plot. It used to be completely understood, but not understood. But I think nowadays, people kind of know what's going on. They just don't know how to stop it. Sorry, Ramesh, I didn't mean to interrupt.
Yeah, it's just that, you know, fluid approximation really shouldn't work at all, right? As the question was, you know, raised, but it works much better than you might have thought. For the conditions that we are dealing with, at least in some set of problems. I'm sure even in astrophysics, there are regions where it just is a bad approximation. The jets, for instance, where the field is so strong, definitely the particles are not isotropic.
Right.
They don't have to be. Everywhere else, it looks like they isotropize. So, yeah.
In the back?
Yeah. You
Nikki.
showed,
Hi.
yeah, sorry. You showed some really cool fiber calculators, and you were mentioning that you have all these cool things in the queue, especially specifically about accretion. What kind of configurations are you running right now? Like, is this all just some certain disks, or?
For the binary black hole?
Yeah.
So to be honest, the first thing we want to do is make sure that the numerical relativity toolkit is working well, and so we're planning to do some just binary black hole mergers in pure GR first, mostly with extreme mass ratios, and we've also been thinking about doing some hyperbolic encounters where computing the waveform from that is very difficult using existing methods. And it could be very important for capture processes in dense clusters. So we'll likely do some pure GR calculations first, and then, you know, so it's going to be 6 months before we're doing a lot with the fluid dynamics, but I think the first thing we'd like to do is some circumbinary binary black hole disks where we're looking at the very late stages of evolution where now GR is starting to play a role, and just looking at how the infalling mass might mess up the waveform you might be observing, and or, you know, whether or not it's going to harden or drive the binary even more, who knows what. I mean, there's some interesting questions to investigate when you have both gas and relativity going on. I mean, it's going to be a mixed master. It's going to be a complete mess. It'll be fascinating. It's going to be a little while. I mean, a little while yet. And David Radice and his group are pushing forward on neutron star mergers. That's their main focus. So I think there's going to be a lot of work done on the Penn State side on pushing on the neutron star merger problem. Hi. Yep.
I have a question that relates to something Andy was asking at the beginning, which is about, you know, saving the frames of the movies and all of this. And so if you actually want to sort of follow some parcel of gas, you know, in this kind of code structure, do you do that, or do you have to specially save some algorithmic way?
Right. It's actually an excellent question, because this approach is, of course, an Eulerian approach where we just have the mesh and we don't discretize on parcels of gas. And so following an individual parcel of gas requires, for example, tracer particles, which would then follow the flow. It's still imperfect because a particle is not the same as a fluid element, which can get distorted and so on and so forth. But nonetheless, it's the best we can do. This particular version doesn't have tracer particles in it, and adding them is a significant effort, and don't really plan to do it. Athena++ has tracer particles, so as I said before, Athena++ isn't going away. If you want to use spherical polar coordinates, you want to do tracer particles, runs great in clusters. But yeah, we're just focusing on some of these other science applications. It'd be great to have that too. And more generally, I think the point is that exascale is probably going to drive us to having more effort in the analysis side of things. We're going to have to think a lot more about that. It's going to be definitely an issue. Yep. Sorry. In the back.
Yeah, so you mentioned that you are moving away from like polar or like spherical meshes to accretion.
Right.
I was wondering, is it because the precision grids are good enough for this type of problems, or are there advantages of exploiting this?
You know, I think like most things, we can say everything, but most things in life, it's advantages and disadvantages, right? So The advantages of Cartesian meshes are, first of all, you can use, they're more accurate because when you have a uniform Cartesian mesh, the truncation error from things like reconstruction algorithms has this fortuitous cancellation, which makes things like fourth order much easier than if you have a non-uniform curvilinear mesh. Getting higher order non-uniform curvilinear meshes is very, very difficult. It can be done, but it's very difficult. So it enables you to go to higher order algorithms very easily. It also gets rid of the pole, which is honestly a huge bugaboo in most of these 3D calculations. So that's great. And it makes, the outcome of that is it makes the time step bigger. That goes back to your, so yeah, we can run to 1,000,000 M pretty easily with these Cartesian meshes because the time step just intrinsically gets larger. No matter, you know, you can de-refine, you can do lots of tricks, but it never ever quite works as well. That's another reason for going to Cartesian. So the disadvantage is that if you have a truly spherical object, then obviously a spherical mesh is a better fit. Then I think you should use these geodesic meshes. They're used a lot in the Earth modeling community. They're a much better way to tessellate the sphere than a latitudinal longitudinal mesh. So if you really want to do a special coordinate system for spheres, I think there's better ones to use than spherical polar. Anyways. And you know, finally, people worry about, well, what about angular momentum, blah, blah, blah. We've done the test, and angular momentum is conserved extremely well, much better than the transport due to MRI and everything else. So the truncation, and the point is that if your solution is so strongly affected by truncation error that it's causing diffusion of angular momentum, you're in trouble anyways, right? You shouldn't believe anything about the solution if it's dominated by truncation error at that level. And just because you conserve angular momentum in spherical polar doesn't mean to say that you don't have truncation error. It's just not resulting in transport of angular momentum, but it's resulting in transport of everything else. So that's a real problem. You know, you can fool yourself into thinking that, oh well, because I'm conserving this exactly, it's much more accurate. That's not necessarily true. The total error is not any better. That one diagnostic may be better. And then lastly, if you want to study jets, you know, and their propagation, then Cartesian is much better because you maintain the resolution versus distance. Moreover, okay, you can either conserve angular momentum or linear momentum, but not both. If you go spherical polar and conserve angular momentum, well then that's a terrible way to evolve a jet, where you want to conserve linear momentum. So, you know, following the propagation of a jet across a curvilinear mesh is subject to lots of truncation error, and you're not going to conserve linear momentum, and the jet will bend. You know, so that's bad. So, you know, like I said, all things in life, it's choices to be made, and for the moment, we're all into Cartesian meshes. And we just have to make sure that we resolve the flow well enough to be sure we're getting the right answer.
Can I ask you to just talk for 1 minute to close about, I guess, the interface between these extremely high resolution efforts? You know, we're at the exascale now. As you said, in 10 years, maybe we'll be somewhere else. And essentially, the layer one step down. So I think for every exascale calculation, because it takes so much work, there's probably a lot of calculations in astrophysics that are one layer down.
Right.
I wondered if you wanted to talk a little bit about, like, how do you balance, presumably this is the most efficient way to do those calculations one step down, as opposed to, for example, like the slightly less efficient algorithm, but how do you see that interface working out in the future?
Right. You know, it's a good point, and that, so in my view, the good thing about exascale is that sort of all boats rise.
Yeah.
I never in my career have ever done a calculation on the whole machine on the world's largest computer. Yeah. I've never done a calculation, so-called hero calculation, where I need everything.
Yeah.
But I certainly benefit from the fact that they built those machines and I could just get 10% of them. All I needed was 10%.
Yeah.
So I'm happy that if I'm using 1% of exascale, that's more than enough for my science. And so yeah, zetascale, that means my 1% is that much bigger. I'm happy with that. You know, why bother to do this at all? You know, I don't think there's a huge game changer moving to GPUs if you have lots of access to CPU. I mean, it doesn't matter. It's computing. You know, this code runs on CPUs, and you can run it on clusters if you want. It's fine. It's whatever. It's just as fast as Athena++. You can just do that. The only thing is, at the national level, for this power consumption reason, You know, the federal government has made a decision that it's only going to build these particular kinds of machines. And if you want access to those machines to do your science,
Right.
you don't have a choice. Right
You
now,
have to apply.
the only big CPU cluster I'm aware of at the national level is a TAC. And you know, that's getting pretty old now, and I don't know how long it's going to continue.
Right.
So the only reason we went this way is because computer time, not the whole machine, just getting, you know, we have an allocation of about 1 million node hours, which is a tiny, tiny fraction of, but that 1 million node hours we couldn't get any other place, you know, so that's why we switched to those, is to get allocations on national centers that, you know, and long term, I'm not sure GPUs are going to,
Be the answer.
and I'm not sure they're going to persist. The only reason, like I said, they're attractive is because they're power efficient. But the computer industry is being driven by power efficiency right now, mostly because of all these mobile devices. So, you know, everyone's building ARM processors. I could well imagine the next 5 years, you'll start seeing clusters built out of ARM processors, which are just as even more power efficient than GPUs, and will be more powerful. And then we're going to go back to, you know, back to x86 C++ coding because all the GPUs will go away. Who knows? I mean, that's the danger here. Is,
Yeah.
So that, you know, again, that's why adopting a common coding style is so important now. I don't care what happens in the future, as long as the Cocos library exists. I think we'll be fine.
Yeah. Interesting. Well, thank you so much.
Sure.
That's like-